I'm a new lead physicist here at Reuter-Stokes, and today we're going to be talking about space weather predictions. So first, I'm going to talk about what are the impacts of space weather, and particularly why Reuter-Stokes or any of Earth customers would care about space weather. And then I'm going to talk a bit about what drives space weather, and then how we, by we I mean the collective community, monitors and tries to understand space weather, and how they use that information to make space weather predictions. And then I'm going to do a brief summary on some work I did on this process in making space weather predictions at a previous job. So first, I should probably define what space weather is. Well, space weather is any extraterrestrial activity which impacts life on Earth or in a near Earth environment. So most of space weather is driven by solar activity. Yes, the sun that gleams down on you, well, pretty well today, is actually a very active thing, and there are consequences beyond just giving us light and heat every day. Fortunately for us, the Earth has a magnetic field and an atmosphere, or we wouldn't exist at all if those weren't true. But because of those two things existing, we were actually protected from most of the activity associated with the sun, and so therefore we can just first off enjoy some of the beautiful things associated with space weather, and that is the aurora. Actually, this whole process is actually driven by particles flying off the sun. So because the Earth has a magnetosphere, those particles fly through interstellar space off the sun, interact with the Earth's magnetosphere, and then fall in through following the magnetic field lines. And as you may or may not know, the poles of the Earth's magnetic field are at the North and South Pole. So that's why you tend to see the aurora near the North and South Pole, and that's why they have these very interesting patterns here. So the high energy particle comes in, interacts with the Earth's atmosphere, excites some of the molecules in the atmosphere, and as those electrons get excited and decay back down, get these nice bright emissions and a very positive space weather effect. And unfortunately, that is not the only space weather effect you get. There are actually pretty severe negative effects as well. So here is the sun, which again is the primary driver of space weather. This is not to any real scale, just for reference. This is the driver. And these are some systems that can be affected by activity produced from the sun. So one of the things that is frequently disrupted during space weather events are GPS and high frequency radio communications. So basically that the high energy radiation interacts with the Earth's upper atmosphere, and both GPS and the high frequency radio signals depend on a certain structure of the Earth's atmosphere in order to operate properly. So any dynamic event interacting with that part of the atmosphere causes interruptions and issues. So if your GPS has directional errors for you driving, the impacts are pretty minimal. But if you're flying a plane and all of a sudden you lose your GPS position, there is a broader consequence to that. And not only are there just atmospheric disruptions, there is magnetic field disruptions as well. So those events that come off the sun, and we'll talk about what they are in more detail later in the talk, but they carry magnetic fields with them. And those magnetic fields disrupt the Earth's magnetic field. And that can cause long-lasting electrical blackouts, and I'll discuss the mechanism of how that happens in a bit, as well as corrosion on oil and gas pipelines. Basically, these both stem from induced currents in those systems. So you induce currents on the electrical grid and in your oil pipelines, which can degrade the pipeline faster than normal. And it also has impacts for directional drilling. Baker Hughes actually has acknowledged this, and there's a study on this, which I'll discuss a bit in this talk. And there's finally radiation impacts. Well, again, mostly we're protected from this due to the Earth's magnetic field and the atmosphere of the Earth. Spacecraft are more vulnerable to this, so that they can be damaged and impacted. Spacecraft can be lost, which is more than just scientific instrumentation. There are critical communication satellites that can be impacted by space weather-related radiation. There's also significant risks for astronauts. So if we plan to continue to put people into space, understanding and predicting when these events will occur is really imperative to any kind of future space travel. And there's a lot of talk. There was significant talk in the industry about, what were the implications for that? Who wants to be responsible for those kinds of predictions? And you can see that, it's you may not have heard of it before, but space weather really impacts a lot of critical systems that we take for granted in our day-to-day lives. It's also kind of an interesting Reuter-Stokes tie-in. Arthur Stokes, who founded Reuter-Stokes, actually built a unique, which you can read as inexpensive, detector for monitoring those atmospheric disturbances that I talked about previously in the upper atmosphere that affect radio signals and the GPS signals. And here's a little clip out of the paper he wrote for this. And that detector actually is the model for the American Association of Variable Star Observers, which is a very large institution, and they make a lot of measurements, and they use this receiver for all of their what's called sudden ionospheric distortions, or SIDS measurements. So the founder of Reuter-Stokes had a kind of an interesting impact on these measurements, and kind of a unique tie-in to Reuter-Stokes, which I don't think a lot of other companies probably can say. But the impacts are more than just, like I said, just the radiation and the atmospheric disruptions. Really, the most critical systems are impacted by these changing magnetic fields. So those rapidly changing magnetic fields, as related to space weather events, can induce currents on transformers, which cause heating and destruction of the transformer in some cases. So here we actually have a step-up transformer at the Salem nuclear power plant in New Jersey. And so there was a well-known, which I'll talk about in a bit more, event that happened in 1989, in March of 1989, where a pretty significant solar event impacted the eastern hemisphere, the eastern United States and Quebec. And because of this, there were induced currents on this step-up transformer to a nuclear power plant, and the transformer was destroyed. You can see this thing is completely melted and disformed, and this repair is $10 million just to replace one of these step-up transformers. And as I understand it, these only are produced really in one location. There's like a 6-month lead time for these parts as well. So, space weather has a pretty significant impact on this particular event here, and can have a particular impact on power stations in general. So this is an example from that exact event. So what we have here is the local magnetic field at 2 different locations, one in Ottawa, Canada, the other in Fredericksburg, Maryland. These little bars here are times of blackouts, local blackouts associated with this event. And then, so you can see here, the magnetic field is rapidly changing. In some of those instances where the field rapidly changes, that's when you see those magnetic field, that's when you see those blackouts locally. So there's a paper written on this relatively recently that just really made this correlation to show, hey, these sudden disruptions in the magnetic field are actually causing blackouts, and we've seen it historically. And this is actually known to be the cause of this particular event caused a 9-hour blackout across Quebec. And this was 6 million people without power for 9 hours in the middle of March, which Quebec is not the warmest place, I'm guessing, in the middle of March still. So that I'm sure was unpleasant for some people. Really, this event kind of prompted a lot of the space weather discussions that kind of happened after the fact. And really, looking back historically, events like this happen about once every 25 years. And fortunately, we kind of missed it this recent go around. But who knows if we'll be lucky, or how long we'll be lucky for it in that regard. And really, when it comes down to fortunate events that we missed, the first known space weather event is called the Carrington Event, which was observed from the ground by an observer named, last name was Carrington. He did this in September 1st of 1859. So he was just sitting in his, I'm sure, very luxurious backyard at the time, looking at his solar telescope and looking at the sun. So this is a drawing he made of the sun. These black spots here are what are called sunspots. If you looked at the solar eclipse a few years back, and hopefully didn't look directly at it, but looked at it through some kind of other device, you may have seen the sunspots out there. There were sunspots on the sun before that, and what those sunspots correlate with our magnetic activity, and we'll talk a bit about how that works here in a bit. But at this time in 1859, no one knew why there were sunspots, and so people would just, our astronomers or solar physicists, would sit there and kind of guess and try to figure out what is happening with them. And he was the first one to notice that during this particular event in September 1st, 1859, that bright lights were visible connecting between these dark sunspots. And that was the first time that had ever been recorded in history. And as soon as he saw it, he ran to tell his friend and just show him. And by the time he got back, they were gone. So he lamented that in his in documentation of that event, but it kind of gives you an idea of how energetic and short these events can be. And then the next day, people started noticing that telegraph wires were catching fire. Telegraph operators were being electrocuted, not fatally, but they were being electrocuted. And even when their telegraph system was disconnected from the main grid. So there was obviously some kind of induction of current going on all over the place. Another real significant events that happened around this is that aurora, which are usually, as I showed in the first picture of this talk, isolated to the poles, were seen in as far south as the Caribbean, which really just means there were magnetic field lines that were open down that far south, which is very atypical. It's very unlikely that we see aurora here in Cleveland. So even getting down even farther near the equator, the fact that that happened shows that there's something really dynamic happened to that event. And then so what people have done is they actually studied, what would be the economic ramifications if, with our current industrial society, which has a lot of electronic components in it, and all of our power grids and all of our power stations, what's the economic impact of an event like that happened in 1859 happening today? And just in the US alone, the economic impact is between 0.6 and $2.6 trillion. However, not all the impacts are, that broad scale thing. There are small events that have real consequences to the everyday operations of even drilling. So Baker Hughes has known this, and they implemented a program with ESA, which is the European Space Agency, to really try to predict the magnetic field in Greenland. And the reason for this is Greenland's actually kind of a bit more north, so it's more sensitive to these sorts of events. So again, they partnered with ESA and used data from a bunch of sources, both satellites and on the ground, to try to see if they can improve magnetic field forecasting, and so that way they could know when they can use the magnetometers on their directional drillers to actually navigate. And so why this matters is solar storm disruptions in this magnetic drilling, and using these magnetic fields while drilling can lead to about a 55-meter error per kilometer during these magnetic storms. So that's a pretty significant error, as you can imagine, if you're off by 55 meters per kilometer. But although the magnetic fields are the kind of the interesting, more dynamic events, because we're not really as well protected from that now as the other things. There are still radiation impacts here on Earth that are of scientific interest, if not necessarily human interest. So here, there actually are a series of neutron detectors all over the world that are tied together in this global system, which monitor radiation from the sun based on basically you have a high energy proton flying in, impacting the upper atmosphere. And when it impacts the upper atmosphere, one of the things that can happen is you produce a neutron, which then also comes down to the Earth, which can be registered by a neutron detector. So here they have an example of just how solar activity correlates with this increase in neutron detection, which is an increase in radiation in the local space environment. So here we have increased rate as a function of the nominal rate. So 0 is just the nominal. And you can see here in gray is the neutron detection on the ground. And then it's going, and all of a sudden, boom, almost a factor of 2 increase in the neutrons detected on the ground by this series of detectors. And then if you look at the X-ray flux from the sun, and why you use the X-ray flux is that actually it's very uncommon to see events on the sun in optical or with the wavelength of light you can see with your eyes. It was a very extraordinary event that Carrington event was. I mean, that's the reason he could observe it. Had it been a nominal normal event, you would never have seen it from the ground. But because it was so significant, he could see it. So when it goes to observing with the more frequent events, you actually go usually to the X-rays or extreme ultraviolet wavelengths to measure these events on the sun, because there's a higher contrast. So nothing else on the sun really gives off as much light there as these events do. So you can use that to exploit that. So as you can see here, the sun's emitting some X-rays, and all of a sudden so this is a log scale. So there's a 2 order of magnitude increase in the X-ray flux off the sun, and that correlates very well with the onset of neutrons in the detector. So why does this even happen? What is happening? What is happening that causes these events, these space weather events, to occur? So there's nothing special about our sun, the typical star. In this core, it is fusing hydrogen into helium. And in the inner part of that core, and out for a little bit, there is a region where photons, gamma ray photons are created and processed. And that is the efficient way of transferring the energy. But as you get a little bit farther out, the radiation processing is no longer an efficient form of transferring energy. And then you start to get convective bubbles, kind of like boiling pots. So you get a more easy way to transfer energy is just to make these little bubbles and move them to the surface. So at that boundary region of plasma, so you have a bunch of ionized particles here and in the outer parts, there are magnetic fields that get twisted and tied up. And as they get twisted and tied up, they emerge into the surface. And then when they emerge, you can see things like sunspots being created, because it's a little bit cooler where those magnetic fields are compared to the outsides. It's really hot in there still. It's just the contrast is such that it's slightly cool there. And then what you'll notice is, okay, so if you start in the center of the sun and go out, temperature is slowly decreasing, as you would expect kind of naively from what you just kind of know in your everyday life, right? If you're near a source of fire or flame and you walk farther away from it, things get cooler. However, once you get into the outer parts of the solar atmosphere, things start getting hot again. So you're at 6,000 Kelvin, which is approximately 6,000 Celsius, or about 1,200 Fahrenheit. You move out into the chromospheric corona, and you actually increase in temperature. That's really unintuitive. And the reason for that is basically that these magnetic fields are injecting extra energy into this layer of the solar atmosphere. And the density is so low there that this increase in temperature is not a temperature that you and I would feel like if you're putting your hand near a flame. It's a plasma temperature. So it's kind of a misnomer that temperature increases, but the speed of the particles do increase, and they do reflect a plasma temperature like that. And you can see there are also these other magnetic features. So you can see traces of features that trace out the magnetic fields on the sun. And here are these flares, which are the brightenings, which is what Carrington had saw in his original event, is the brightening associated with these magnetic field events that happen on the sun, and they're kind of they're the initial observation of space weather activity. So the flares, like I said, are the brightening of on the sun, but really what drives space weather is the CME, or coronal mass ejection. This video is lagging, unfortunately. Yeah, well, that's unfortunate. Okay, so you may or may not have seen it. So there was you can see here that there's a bunch of, this is actually real data from the sun. So this is real observations from the sun. You can see here is hot gas tracing the magnetic field lines on the sun. And this gas here actually is gas that was ejected from the sun, that it fell back under its gravitational pull. So this is observations. These observations like this of the sun are taken in 8 different wavelengths of light every 12 seconds. So this is continuous data from the sun to measure and try to understand its magnetic fields, because actually these eruptive processes and what's going on here are not well scientifically understood, which means that really someday, if someone can figure out how this all works to high detail, there's probably a Nobel Prize in there for that someday. So here again, we have the material. It's sitting here, and then you see this brightening, that's the flare. Then you see the material being ejected out. This is the coronal mass ejection, or CME. And these are the particles that are really going to drive, the particles and magnetic fields that are tied up in that are going to be what drives space weather. And the properties of these types of events are such that the average CME has about 1.6 billion tons of material and travels at about 1,000 miles per second. And it's worth noting, flare and CME are not the same thing. Not all flares have CMEs, not all CMEs have flares. So the brightening and the ejection of particles are 2 separate phenomena, and sometimes you can have one without the other. So what happens when that material goes off into space? Well, if it escapes the local escape velocity of the sun, so it can get out of its gravitational pull, it just flies out into space. So here's a little cartoon kind of what happens. So you have the sun, material that was being ejected, kind of like we saw in the previous video, and then it heads out into space. And sometimes it heads out into space to Earth. So here we can see an image here of the sun. So this actually occults the sun. So it's kind of like a permanent eclipse on the sun. So you can see the outer atmosphere of the sun. And it was sitting there observing the sun. One of these coronal mass ejections happened, and boom, this detector was completely saturated with particle hits on the detector, which kind of made these observations useless. But you can see that there are actually other detectors that are used to actually monitor the number of particles that are incident. So here, a little proton detector, and you can see during these events, the high energy, so these are 150 and 10 MeV particles, increased by 4 to 5 orders of magnitudes. And these are called solar storms, or this particular event was called the Halloween solar storms because it happened on, as you can guess, October 30th or October 31st of 2003. So ideally, what you could do is kind of like what you see in regular weather forecasts, is model what the sun is going to do, run that model, and then these flares occur, and you can predict all the space weather that there is, and you can know what the environment's going to be like. Well, things unfortunately aren't that simple, because the mechanisms really for driving space weather on the sun, I can say they're magnetic fields, but exactly how and why those magnetic fields respond that way and why all that happens is still very much an area of active research. So you really can't build these models in any real way. And in the way that they're built now, they're very inefficient for space weather prediction. So here's an example of a modeled ejecta from Torek et al. Actually, there's a division called Space Predictive Sciences that they do coronal modeling every day. But their models really don't either have enough resolution to get the finer detail right, which matter in space weather prediction, or if you try to get the finer detail right, then your time for computation is longer than the time it actually interacts in space. So, right, if you're trying to measure something that happens on the order of minutes, and it takes you hours or days to model that, you're never going to be predictive. And that's currently the state of what these models are like. But in the future, hopefully that's what it's like. And so this here, the intensity here lines are density lines, and these wrapped up things are the magnetic field. So ideally someday the sun will be so well modeled that you could just know exactly what the space environment is going to be like everywhere, and then we could be sitting here at Earth saying, okay, we know the sun's going to do this day, we'll protect ourselves this way or that way, and such and so forth. But that is not now, and that is kind of a far time from now. So instead, what you're left with is to record data and as fast as possible transmit that data to Earth and try to figure out what's going on. So to that end, NASA and NOAA have a series of space weather monitoring systems. Those systems, they measure the plasma, and they also measure what the composition of the solar wind and all this ejected material looks like. And in doing so, they get an idea of what the space weather environment is going to be like here at Earth. So a particular interest in this model is, so here we have these 4 satellites sitting here at L1, which is called the ground point 1. It's just an area where the Earth's and the sun's gravitational pull is roughly equal. And so you can stick a satellite there and get an idea. You can stick a satellite there and you can get a really good, stable configuration. So you can let satellites orbit there with minimal amounts of energy, right? So you're not spending fuel or setting up these huge satellites, which then cost more fuel to send them up. So it's an inexpensive region to let satellites sit in orbit. And in doing so, you sit about an hour to 3 hours upstream of any particles coming off the sun. So if you have these satellites sitting here at L1, the material gets shut off from the sun. It could take a day or 2 or 3 to arrive. And then a couple hours before, these satellites will all see that event come through. It'll come through, it'll hit the Earth's magnetosphere. That will be processed by the Earth's magnetosphere and then end up causing some kind of either magnetic field disturbance on the ground or some kind of radiation event in the outer parts of the atmosphere. So the fact that there are 4 of these are interesting, and that's kind of where my impact comes in here on this. But there's also something interesting that's happened recently, is that the Solar Orbiter and what's the Parker Solar Probe are 2 new spacecraft within the last few years that are now flying closer to the sun than any other spacecraft has done previously. And actually, fun fact is that I actually got to do a little bit of babysitting of one of the instruments on the Parker Solar Probe, which actually ended up being the closest man-made object to the sun, and is actually by default from doing that the fastest man-made object ever made. So that's kind of a fun little tie-in. And I'm going to talk about that instrument because it has a pretty significant impact in both space weather predictions and space weather monitoring, and really understanding what kind of material is coming off the sun and what its properties are. So there really are 2 primary measurements for space weather. You have Faraday cups, which I'll talk about here in a bit, and magnetometers, which just measure the magnetic fields in space. So the Faraday cups work like this. They're actually very similar to the Faraday cups that are on the newly acquired RGA that we got for the PMT project. So here is an example of the energy spectrum that you might expect from solar wind particles. So you have low energy, relatively low energy particles, and much higher energy particles. So a Faraday cup works by you have a couple screens that are well grounded, and then there's a AC voltage or an oscillating voltage screen. And so what happens is, because there's a potential here, the low energy particles can't get through, and then they're reflected back and not collected by the cup. As you oscillate in internal energy, or voltage, so if you go between here and here, the low end, right, all of those particles from that have that energy will pass by. On the high end, they'll all be deflected out. And so the number of particles in a given bin is proportional just to the up and down oscillations here. And the current is then collected by a plate at the bottom. So every particle gets by, gets hit, lands on a grounding plate, electrons get driven in here, and you can measure that current to get an idea. We'll get the exact number of, well, in this case, what are protons impacting the detector. And from this, you can understand the plasma parameters of the material being produced. So things like speed, temperature, density, all this information can be gleaned from an instrument like this. And using instruments like that and some imaging instruments, people currently do make predictions of what the space weather conditions will be like. So this is primarily driven by NOAA, which is a National Ocean and Atmospheric Association. They create near real-time predictions of the solar wind at Earth. This plot here shows here Earth in green. These two things are different spacecraft, and one of them actually isn't operating anymore. So these predictions have issues with being as good as they could have been. These also depend on those L1 spacecraft that I talked about previously to get the better predictions about a couple hours ahead of time. So from those spacecraft all combined together, you can get things like what the plasma density is. So larger particles, larger density of particles means there's more likely that you're going to have a significant event, and also faster particles. So if there were any black points or maybe even white points on these plots, you'd expect some kind of space weather related phenomenon. Maybe small, but it would be impactful. But these are all pretty small events. Turns out the sun's not very active right now, following its normal cycle, so it's not going to really have anything interesting on here for the next few years. So the interesting point about all this is all these predictions are built on a fleet of spacecraft that are not really in a great state. The newest one, most recently launched one, has a series of issues. It was recently out of commission for 6 months, and ever since its launch, it's had a number of issues actually collecting and processing data. The next youngest one after that one is 25 years old and well beyond its operational lifetime. You don't necessarily want your spacecraft, you don't expect your spacecraft to live for 25 years. That's a very long time. So we're kind of in a precarious situation when it comes to this. So what I did is I also took data from those spacecrafts and saw if I could put a small sliver of my imprint on these space weather predictions. So what happens is, because there are 4 spacecraft currently at the L1 point, which is again about an hour to 3 hours ahead of Earth in the solar wind propagation. What I worked on with the PI for this project was trying to use those 4 spacecraft to develop a system to make more accurate predictions of what the plasma is going to look like at the front of the Earth's magnetosphere right before it starts getting reprocessed by the Earth's magnetosphere. And because there are 4 spacecraft, there's actually an interesting number. Because there are 4, you can actually create a plane and propagate that plane forward in time. But the problem with that is now you have to match events. And because these spacecraft are oriented in space at different times, that you actually expect the propagating front to pass them at different time scales. So if you can match those events, then you could make an accurate prediction of what that plane is going to look like as it interacts with the Earth's magnetosphere. I do have a question, so maybe I see if I can get this here in a second. So using that, I was actually able to match those together using a algorithm called dynamic time warping. That's because we actually found it kind of by accident. Was talking with someone about a different project, and they mentioned this algorithm, and it was actually perfect for what we need here because these spacecraft actually have different cadences. They have different timings, like I mentioned before, and sometimes there actually are small local events that will happen in one spacecraft and not the other. So you can kind of see that here. So this black here is one spacecraft, and then you can see it dips down here in the flow speed of the solar wind. So the solar wind had a low speed environment for a little bit before jumping back up. But if you see the other spacecraft, they didn't see that. So the way you can get around this is dynamic time warping allows like compression of points, so you can kind of basically just skip that feature. So that was kind of fun in implementing that. And I guess the question is, did this work? Were the predictions in any way better than what was already being gleaned from just one of these spacecraft at L1? Because that's the normal operating mode is, hey, we'll just use one and see if that, and use that for our prediction system. So that this was the novelty of this one, was trying to use 4 and match that up together and see if there were any real predictions that could come out of it. And the answer was yes. So we studied a number of events, but I just showed one here for an example. So the state of the art for the prediction of the plasma parameters as they impact the Earth's magnetosphere are driven what's called by the omni prediction system. So you can see real measurements of a spacecraft right outside the Earth's magnetosphere here in yellow. In gray is the omni predictions, and in black are the predictions that I built up for this particular system. You can see here, this particular event, the omni predictions were ahead by about an hour and a half, hour 15 minutes there. So those are pretty substantial deviations, and it predicts this huge feature here, which is not seen in the data. And there's actually a reason my prediction breaks down there is because this was actually a local event. So the spacecraft they used was the only one that observed this event. And so because they used it, they made a prediction that something was going to happen there and didn't happen. Whereas if you were using the multiple spacecraft approach, it said, hey, there's some non-physical configuration going on right here. There's no way we can make an accurate prediction this scale. Let's skip it and move on. And you can see that it predicts this deep dip at a better time than the omni prediction. It predicts this increase here at a very good time, and this one as well. And there's a similar events propagation for a number of the events that I worked on for this prediction system. So you can see that there was some benefit to this, and there would be a very interesting model going forward. And so on that note, that's kind of the limitations for this is, unfortunately, this process we only currently have really the magnetometers, for what it's worth, were the most important system in these prediction systems because they have a higher cadence and there's less bias from system to system. Using them would have been ideal. Fortunately, only the 3 of those 4 spacecraft had magnetometers. So the 4th one only had the plasma parameters for the matching. So that was really our limiting problem in the prediction system. There's also kind of there are 4 spacecraft there right now, but again, there are in varying degrees of decay. So this kind of system would be limited by that. And so we spoke with some NOAA higher ups during an AGU conference about this. And I mean, I think there's interest there, but financially it's kind of going to be expensive to do what you really want to and kind of need to do is build like a fleet or a swarm of spacecraft that you sit both near Earth and at the L1 point, and then actually on the ground as well. There is a lot of need and interest in collecting ground data to understand how something at the top of the atmosphere affects something on the ground, or sorry, at the top of the magnetosphere and in space talks to something on the ground. And having this kind of swarm and data processing center is really, in speaking with in those people, that's really where they want to go. It's really just going to depend on can they get there or not. And so that brings me to the end I appreciate everyone's time and energy sitting through this. So now I will answer some questions. Okay. So I have a question from Jeremy. It says, how would you prevent space weather events from damaging equipment like electromagnetic interference and use Faraday cages? So yes, you can shield some equipment from the magnetic field problem, but a lot of times for the power grid, there are precautions they can shut down for short periods of time. That's kind of the normal operating procedure as I understand it. This is not my area of expertise, I warn you, but my understanding is there's some kind of shutdown sequence you can do locally that prevents a lot of that damage. And predicting when those are going to happen gives the utility time to appropriately shut down and do the things they need to do to keep their equipment safe. Does that answer your question, Jeremy?
It does, Jacob. Thank you.
Okay.
And also, Alex had a comment below, which agrees with your answer pretty well. He says, avoid loops that can take EMI and turn it into large currents.
Right. Okay. Great. Yeah, I hadn't read that comment yet. Okay. All right. Are there any other questions or comments at this time?
I've got a question.
Okay.
This is Kevin. You showed a plot that showed the neutron flux from the atmosphere during an event and overlaid with with an X-ray flux. Mm-hmm. Are those X-rays produced also in the atmosphere, or are they produced at the sun?
They are produced at the solar surface. So you're probably noting that the time difference is very small.
Yeah.
Yeah. So you can accelerate particles in this quite near the speed of light.
So the protons that generate neutrons in the atmosphere are traveling nearly the speed of light.
That's correct. Yes, that's solar energetic particles. That is where that field comes in, and it's not a large number of them, but there are a few that can happen in this regime. This is not really what drives the primary radiation flux. Well, yeah, it's separate from that main CME body of particle radiation.
I would expect that protons coming from the sun would have energies, kind of comparable to the temperature where they're produced, right? So I think the hottest you had, or in the coronosphere, is like 6,000 Kelvin or something, right?
Oh no, in the coronosphere you can get up you can get up to several million degrees.
Ah, okay.
Yeah, it's like
right.
Sorry. Yeah, so like 20 million in a flare, you can get plasma temperatures that hot.
Okay. All right. I have one more simple question, as long as I'm unmuted. Is the change in the location of the Earth's poles significant enough to, like matter in our lifetimes?
What are you saying?
Respect? So if the magnetic field, if the poles are moving, well, they are, right? The poles are moving, so that's changing the orientation of the Earth's magnetic field. Is that going to change the effects of solar, the solar wind, on the Earth or on satellites in orbit? Is their weather going to change, or the way they experience the solar wind going to change because of the changing magnetic field of the Earth?
So I'm not an expert on this, but my impression from listening to some discussion on how the magnetic field matters. So I don't know how. My understanding is the changes that are happening right now are very small and will not make a significant effect. I don't have any idea what happens if the orientation flips like it does every, I think 50,000 years or so, what that's going to do, and I think that's one of the things that people are concerned about with the flipping of the magnetic field. But I don't have an expertise to really comment on that in any great detail.
Magnetic poles are flipping every 600,000 years. It's a multiple events in geology, as I remember. Then on one side, during flipping, we can save on night electricity. I mean, because it's the light not on the poles, but in the tropical area. And I want to thank for very impressive video of the sun's surface. It's really amazing. And back to the magnetic storm. In 2006, I participated in Energex in Stavanger, Energex 2006. We discussed blackout process in Italy, Southern Europe. And a few questions were, what if happens with blackouts? And the recommendations were the blackout usually it's when magnetic field total change its area in square miles or whatever, multiplied by speed of changing of total magnetic flux. Total magnetic flux may be very small. It's a part of a magnetic field, but the area is huge. And we have single turn electrical grid around this area, and they may be a million volts and a huge current. So recommendation was to cut ring connection and go to star connection to prevent closed loops. And the prediction of whatever is coming, magnetic storm is coming. If you have a few minutes, you can change the position and distribution of electricity just to use star configuration. It's extremely important. Thank you very much for a very good presentation. Thanks.
Well, thank you for explaining that in detail. I did not know the inner workings of that. That's very interesting. Okay, then I think we can go ahead and close now, unless there's any more questions. Okay, let's go ahead and close this. I appreciate everyone's time for this, and hope you enjoyed it.
Thanks, Jacob. Great presentation.